All right, guys, so far in this unit, you should have several skills. First of all, you should be able to understand the meaning of and should be able to calculate the K value, the equilibrium constant. You should be able to understand the meaning of and calculate Q values, the reaction quotient. The equations are exactly the same. Remember, K is when we know we are at equilibrium. Q is when the system may not be at equilibrium. And you should be able to compare Q and K. And that should help you understand what the system will do to reach equilibrium. Remember, all closed systems will reach equilibrium eventually. So by comparing Q and K, you should be able to determine if the reaction must progress forward or backwards in order for the system to reach equilibrium. I'm not going to go back over that, but this is where we are so far. And today we're going to talk about probably the most important part of this unit, and it's a little bit more conceptual. It's related to the math of everything, a little bit more conceptual, and it's known as Le Chatelier's principle. Le Chatelier's principle is basically this. If a stress is applied to a system at equilibrium, so we have a system at equilibrium, and we apply some kind of stress, that system will respond by shifting its equilibrium position to relieve the stress and reach a new shifted equilibrium. So the idea is that we have something at equilibrium. We apply a stressor to that. We stress the system. When you add stress to the system, the equilibrium will shift. We are no longer at equilibrium. So no longer at equilibrium. And the system is going to have to respond in some way to relieve the stress and reach equilibrium again. When it reaches equilibrium again, I say it's a new shifted equilibrium. That means the equilibrium position will be shifted. In other words, the K value can't change. There's only one way to change a K value. We'll talk about that later. But the K value cannot change. Instead, the concentrations of reactants and products may have shifted around. Okay? So to understand this, we really need to understand what is meant by stress. A stress is any change that we make to the system. It could be a concentration change. Maybe we add more reactant or product or take some away. Maybe we have a pressure or a volume change. Maybe we increase the pressure of the system. If it's gases, right? For gases, these things matter. Maybe we increase or decrease the pressure. Typically, we can do that by changing the volume, right? You guys know that at a constant temperature, pressure and volume are inversely proportional to each other. So if I decrease the volume, that's going to lead to an increase in pressure. Just some things to remember, these gas laws. So change in volume or change in pressure could shift my equilibrium, right? Because remember that equilibrium for gases can be described by pressures as well as by concentration. And then a temperature change is a stressor. But this is very, very important. Temperature change and temperature change alone may result, actually will probably typically result in a changed K value. If you have been listening at all, you have heard me say many times that this equilibrium constant K is tied to a specific temperature for a specific system at a specific temperature. So if we change the temperature, now all of a sudden we've changed the K value. And you guys know that different K values have different meanings. A very small K value means that the forward reaction is not favored. We hardly make any products. A very big K value means that we mostly make products. And an intermediate K value means that we have some mixture at equilibrium of reactants and products. So by changing the temperature, we could get the system to shift one way or the other and actually change that K value. Only by changing the temperature do we change the K value. If we change the concentration, change the pressure, do something else, that's not going to change the K value, but it will change the equilibrium position, the mixture, the ratio of concentrations or pressures of products to reactants, okay? So the idea is that the system will always shift to try to relieve the excess stress that we put on it. Just kind of, I mean, it's kind of common sense, right? It's almost like human behavior. If your body starts to get too warm, your body will naturally shift its homeostasis to try to cool your body down and bring its temperature back to normal, right? You're going to start sweating. You're going to start to move towards where there's shade, etc. You want to relieve that stress of the extra heat, right? If your body's getting too hot. Same exact thing for chemical systems, okay? So we really need to look at some example problems. Here is a really good way of visualizing the Chatelier's principle. It's all about restoring balance. If you're familiar with the idea of homeostasis from biology that I just mentioned, this will probably make more sense to you. So at equilibrium, here's a chemical system that's reversible. N2 plus H2 yields ammonia. We've seen this several times. At equilibrium, we're saying that these things are at a balance. So if we tip the balance, if we add a stressor, the example here is that if we add more to the left side, that's a stressor. Maybe we inject more nitrogen gas, more hydrogen gas into our system. Then all of a sudden we have caused more reactants to pile up. The thing is going to tilt like this, right? Well, how can we get it to tilt back the other way? We have got to remove those excess reactants and make more products to tilt the scales back the other way, to cause it to swing back this way, to reach equilibrium again. So if by adding more reactants to restore balance, the system will respond by making more of what's on the right, products. So you can think about this whole thing like a seesaw and how the seesaw gets tilted based on the stressor. Here our stress is adding more reactants. The system, in order to restore balance, to swing this back the other way, is going to have to make more products. So we would say that the Chatelier's principle tells us that if we add more reactants, we would say that the reaction will shift to the right to form more products. Therefore, restoring balance, okay? The exact opposite is true. If we add more products now, then it is as if we've added more to this right side of the seesaw. It tilts this way. We've added more products. How can we bring the system back to equilibrium? Well, we've got to put more stuff on the left side and take some stuff away from the right side. How are we going to do that? We're going to shift the reaction back to the left. The reverse reaction will be favored now. Okay? So these are ways for us to shift the equilibrium system, to shift the position, to shift the reaction, favor the formation of products or the formation of reactants. Whatever you do to the system to stress it out, the system will respond by doing the opposite, basically. Okay? That's the Chatelier's principle. Whatever you do to the system, whatever stressor you add, the system will respond by doing the opposite. Here's something that's interesting that we haven't seen before. This system has heat on the right side. In other words, they're treating heat like a product. This is going to be hugely important for you all. When heat is like a product, that means that the reaction is exothermic overall. So this makes sense. Exothermic spits excess heat energy out like a product. So exothermic, we can treat heat like a product. If a reaction is endothermic, we're going to be able to treat heat like a reactant. So this is an exothermic reaction because heat over here is shown to be a product. It's spitting excess heat out. If heat had been written over here, and sometimes it's written like delta H. You guys know that heat is enthalpy, and enthalpy is delta H. So when delta H is as a product over here, the delta H of your reaction is negative. Exothermic, remember, has a negative delta H. So we could say over here that we are adding as a product that amount of delta H. Does that make sense? Endothermic, of course, means that we have a positive delta H, and then we would write it over here as a reactant. Well, why is this important to think about heat energy like a product or a reactant? Because it can help you understand what's going to happen if you change the temperature. Let's say in this example that we take our system and we decrease the temperature, we lower the temperature of the reaction. We lower the temperature of the environment that the system finds itself in. Well, that's a stressor. What is the system going to want to do? It is going to want to bring the temperature back up. How can it bring the temperature back up? It can make more heat. Heat is a product. So if we lower the temperature of the reaction, the system will respond by making more product. So the system will shift to the right in response to our stressor. It's just exactly like we took away some product. By taking away some product, we tip it this way. How can we get it to tip back the other way? We need to remove reactants and make more products again. So we need to shift the reaction to the right. What if we increase the temperature in which the reaction is occurring? That's like we are adding more heat energy. We're adding too much product. So now my seesaw is tilted like this. What's the system going to do? The system will, of course, respond by shifting to the left. It's going to consume that excess heat that I have given it, just like it would consume excess product I've given it, to try to shift this back to equilibrium by consuming more products, making more reactants. All right? And of course, changing the temperature is going to change the K value. Don't forget that. So we're going to practice this a lot. This is hugely important. The College Board is obsessed with Le Chatelier's principle, asking questions about it. So let's dive in with some somewhat complicated examples. Okay, let's wrap our heads around this question. Okay, so we have this hypothetical reaction between gases, and it's taking place in a closed 2-liter flask at 298 Kelvin. That's about room temperature, right? 25 degrees Celsius. The graph below represents the change in the number of moles of each gas in the flask over a period of 20 minutes. So let's just make sure that we can wrap our heads around the graph. A and B are reactants, so of course their number of moles will be decreasing. And AB2 is a product, so of course it's going to be increasing. And then something happens at about 5 minutes, doesn't it? What happens at about 5 minutes? It looks like the number, or we could even say the concentration, because my volume is not changing, it's a closed rigid 2-liter flask, the concentrations become constant. What happens in a reaction system to make the concentrations of reactants and products not change? That's equilibrium, isn't it? That's what the first question is asking. How long in minutes did it take for the reaction to reach equilibrium the first time? Well, the number of moles of reactant and product stay constant. So I know that happens at 5 minutes. That's the meaning of equilibrium. Remember that equilibrium is when your system comes to a point where no change occurs anymore. Okay, write down an expression for the equilibrium constant K for this particular reaction. That's going to be pretty simple. I know that K is going to be equal to the concentration of products, so AB2 raised to their stoichiometric coefficient of 2, so raised to the power of 2, divided by the concentration of reactants raised to their stoichiometric coefficients. A is raised to the first power, B is going to be raised to the second power, just like that. Now I could actually calculate a K value, couldn't I? Because I know the equilibrium concentrations. Remember, this K is only for equilibrium. Well, at equilibrium, I know that AB2 right here has 0.8 moles, and therefore the concentration would be, concentration is moles per liter, 0.8 moles divided by 2 liters, that would be 0.4. The concentration of B2 right here, 1.2 divided by 2 would be 0.6. And the concentration of A2 is 2 moles divided by 2 liters, that would be 1 molar. I could plug all of those into this equation and actually get a real number for my K value. It would be the concentration of AB2 raised to the second power, so that's going to be 0.4 squared divided by the concentration of A2 raised to the first power, that's going to be 1, times the concentration of B2 raised to the second power, that's going to be 0.6 squared. Looks like my K value is not too big and not too small, 0.44. Just like that. It is kind of small, it's not like huge, and you can see that makes sense because I've not made a huge amount of product. So I would not say my product is favored right now. Instead, I get this significant mixture of reactants and products. All right. Question 3. Calculate the concentration of each of the reactants and the products using figures from the graph between 5 minutes and 10 minutes, and hence calculate the equilibrium constant for this reaction. Oh, we just did that, didn't we? Calculate the concentrations between 5 and 10 minutes. I did that. Concentration is number of moles per liter, and then actually find the K value. So first, question 2 just asks us to write an expression for the K value, an equation that we could use to solve it. And then question 3 asks us to actually solve it, and I just went ahead and solved it. So there's the K value. State what a low K value indicates about the yield of a product for a reaction. Oh, we've already talked about that. This is kind of low, so I know that I don't get a lot of product. Why is it not possible to calculate K using figures from the graph during the first 5 minutes? So during the first 5 minutes, I was not at equilibrium, was I? My number of moles were actually changing. The rate of the reaction had not equaled out yet. So the number of moles were changing. I did not have equilibrium concentrations. K can only be calculated from equilibrium concentrations. And my concentrations were changing, so I was not at equilibrium. I could not calculate K. That's question 5. Question 6, the Chatelier's principle says that a system will shift to relieve a stress put on it. And then 7, this is the big important question of this whole slide. At 10 minutes, we see something happen. At 10 minutes, something happens to undo equilibrium. Does that make sense? I was at a nice equilibrium with constant concentrations, constant number of moles of reactants and product, but then all of a sudden some change happens. I break out of that equilibrium. The only way you can break an equilibrium is to apply a stress. So some stress has been applied. And let's think about the result of this. As a result, the stressor caused my system to shift what way? It shifted to the right. I made more product. I consumed more reactant. So I caused some stress that caused my system to respond by shifting to the right, by making more product and consuming more reactant. My reactants go down, my product goes up. Do you see that? Okay. So it actually tells us what stress there was. It says the temperature of the flask was increased. Using Le Chatelier's principle, determine if the production of AB2, in other words, this reaction, is it endothermic or exothermic? Well, I know that the stress right here at 10 minutes, I increased the temperature of the flask. In other words, I added extra heat energy. And I can see that by doing that, my system responded by making more products. So remember how we said we can think about exothermic or endothermic processes? We can think about them as heat being a reactant or product. Okay? So think about this. If heat was a product, that is exothermic. And if I increase the temperature, I add extra heat, that would be like adding extra product. That would be like, if this is my equilibrium with reactants here and products here, that would be like breaking that equilibrium to add extra product and weigh down that side of the scale. I've tipped the scale to favor the products. How can the system shift back? By making more reactants again, right? Is that what happened? No. By adding extra heat, I made more product and consumed more reactants. So I know that heat cannot act like a product. I know it's not exothermic. In other words, I know now that the reaction is endothermic. This is hugely important. Everyone needs to make sure that they pause and they understand what's happening. I'm saying that heat energy can be treated like a reactant. I know that because whenever you add excess reactant, the system will shift to tilt the scale back towards the product side by making more products. I need to make more products, and that's exactly what happened. I added extra heat energy. I increased the temperature. I added extra heat. In response to that, I can see on my graph that I ended up making more product and consuming more reactant. Therefore, I know heat must be acting like a reactant. Therefore, I know that it has to be an endothermic process. I'll say it one more time, and then if you don't understand, you need to watch this until you do, and you need to ask me questions because this is hugely important. I notice that at 10 minutes, equilibrium is broken. I add some stressor that causes the system to respond to relieve the stress by consuming more reactant and adding and creating extra product. So I know right away that I must have done something. I must have caused a change that tilted the scales toward the reactant side, just like this. And the system's going to respond by tilting the scales back by making more product. Well, they told me what I changed. They said that we added extra heat energy. We increased the temperature of the reaction flask. Therefore, I know right away that heat must be acting like a reactant, and I know therefore that the reaction is endothermic. Okay? Now, remember that I told you that by changing temperature of the reaction system, by adding or taking away heat energy, we can actually change what the K value is. So I would like for you guys now to calculate what the new K value is. If we truly did change the temperature, we should have a new different K value now. The system reaches equilibrium again in about 15 minutes. That's when the concentrations stay about the same. So let's see if we can figure out what those concentrations are. It looks like B has a concentration of 246.6 divided by 2, which is going to be 0.3 divided by 2 because it's a 2-liter flask. AB2 has a concentration of 1.4 divided by 2, which is 0.7. And then A2, it reaches a molar amount of 1.6 divided by 2 would be 0.8. So same equation for our K value. We reach a new equilibrium at 15 minutes, so these concentrations can help me find the new K value. The concentration of AB squared, so I might call this like K prime or something, my new K value at this new higher temperature. My new K value is going to be the concentration of AB squared, so 0.7 squared, divided by the concentration of A2, which is 0.8, raised to the first power, times the concentration of B2 raised to the second power, so it's going to be 0.3 squared. And my new K value, therefore, is 6.8, which is much, much larger than it was before, which makes perfect sense because you can see now by far I have more product than reactant. B went down dramatically. AB2 went up dramatically. So it makes sense that I would get a larger K value now. Again, the only way to change the equilibrium constant K for a reaction system is to change the temperature, and that's what we've done. So hopefully you can see that. So big ideas here is that from these graphs we can find the equilibrium concentrations, calculate a K value, and then we can analyze what happens to break equilibrium and to be able to predict interesting things about the system. We were told that at 10 minutes we change the temperature, we increase the temperature, and we can see that as a result the system made more product and consumed more reactants. So increasing the temperature, we must have added a stressor that can be thought of as adding extra reactants so that the system responded by consuming those excess reactants we gave it. So heat must be acting like a reactant. The system must be endothermic. Let's look at another example. We're going to look at a lot of these. Okay, so this one is pretty simple. There are no questions here. I just want to go over it with you. So here's our reaction system. Once again, the formation of ammonia. And you can see that we have an initial equilibrium. And what we could do is we could calculate the K value. I don't want to take the time to do that because we've done it about 1 trillion times. We know the K value would be the concentration of NH3 raised to the second power divided by the concentration of N2 times the concentration of H2 raised to the third power. Oh, why don't we go ahead and calculate it? It might be kind of fun. The concentration of NH3 here at the beginning looks like it's 2. So I'm going to get 2 squared divided by the concentration of N2 is, what do we think that is, about 0.5 times the concentration of H2 raised to the third power. So that's going to be 3 to the power of 3. And we can get the K value, and I get a K value there of 0.296. Which kind of makes sense to me because I do have quite a bit of H2 reactant here. Okay, anyway, you can see that at this time we add a stressor because the system, my equilibrium is broken because the system shifts. And you can see that suddenly my concentration of N2 jumps up. So the change that must have occurred is the sudden addition of N2. Maybe I inject into my reaction flask some excess N2. And that is a reactant, right? I have added excess reactant. That's a stressor. How's the system going to respond? It's going to consume reactants and make more products again. And we can see that's exactly what happens. By adding excess N2, you can see that then N2 starts to drop again. I consume that reactant. H2 starts to drop. I'm consuming that reactant. NH3 starts to rise. I start to produce that. So once again, the Chatelier's principle tells us that the system will respond to undo the stressor that we just added. We just added excess reactant. The system will consume reactant, make more product again. Okay? We can see that the new equilibrium that's been reached, because we haven't changed the temperature, the K value should be exactly the same. And this is going to be a little bit difficult to calculate, but if you do take the time to calculate, just difficult because we can't quite see like what these values are, but if you do calculate that, you should get the exact same answer. The Chatelier's principle, we added excess reactant, the system responded by consuming reactants, making products until it reached equilibrium again. Now, there's another way of thinking about this that I really need you guys to pause and make sure that you understand as well. Remember that we have a more general expression for K for when we don't necessarily know if we are at equilibrium, and that's Q. So let's say that I make this or let's say that I write an expression for Q now. Remember, it's the exact same equation, right? So here at the beginning, when my system is at equilibrium, I would say that initially at equilibrium here, I would say that Q is equal to K. That's true at equilibrium, right? But then what happens at this time when I inject excess reactant? When I add excess reactant all of a sudden, then for that brief moment, what's going to happen to Q? Q is now a smaller number, isn't it? Because I've just increased the denominator. So Q gets shifted and becomes less than K. And what do we know is true of a system when Q is less than K? How can we bring Q back up to K? We say that the system proceeds to the right. The system shifts to the right. What does that mean? We go and we make more product. The forward reaction is favored. That's exactly what we see happening. Reactants get consumed, product gets produced. So we can think about this, Le Chatelier's principle, when we change amounts like this, that's a stressor. We shift Q away from K, okay? Listen, here's a really simple way of thinking about it. Think about a chemical reaction system like a ball rolling down the like a marble that you drop into a bowl or a cup. Okay, so think about the marble as your reaction system. So here's my cup, here's my marble. Let's let the left over here represent reactants. Let's let the right represent products. Okay? If I drop my marble, it's going to roll down and it's going to swing up here and then come back and forth, back and forth, back and forth, but eventually it will settle down right in the middle. That represents equilibrium. Okay? An equilibrium that has a large K value, that is like a cup that is shaped like this, where the lowest elevation, the lowest point of the bowl is like over here on the product side. So where is the ball going to settle? Close to the products. What if my K value is really small? That represents a system that favors reactants. So that is like the lowest elevation of the cup being over here close to my reactants. And the ball is clearly going to settle like right here. Okay? So that might be a little bit abstract, but for those of you who are more visual, you can visualize this. Here's the important thing, guys. If I think about my chemical reaction system like a marble that I am rolling, and let's say that it's at equilibrium down here. It's at equilibrium. Nothing is changing, nothing is moving, nothing is happening. And then all of a sudden, I add more reactants. That is like I come in here and I forcibly move the ball back up here toward the reactant side. Well, clearly, what is the system going to do? That ball is going to roll back this way, swing up here, and make more products. All right, so this is just another way. You can think about it like the seesaw thing. You can think about it like a marble rolling in a cup. You can think about it like a pendulum. Pendulums, you know, when you leave them by themselves, when they reach physical equilibrium, they're hanging straight down. By adding more reactants, it's like we bring it up here to the left, and then what's it going to do? It's going to swing back to the right. All right, so whenever you add a stress to a system, the system is going to respond by doing the opposite. Same exact thing with chemical systems. We add more reactants, the system is going to respond by doing the opposite. In this case here, we've added more reactants, the system is going to shift to the right. Another way of thinking about that, we have made Q less than K. We have increased the denominator here. We've made Q too small. We know that systems will proceed until Q is equal to K. So how can Q become K again? We know the system will shift to the right. Okay, so there's many ways of thinking about this Le Chatelier principle stuff. Pick your favorite way. Hopefully I've mentioned a way that resonates with you or makes sense to you. Let's keep working through some examples. Okay, this is a great one to go over. So here's my reaction system. COCl2 is a gas, and it decomposes to form chlorine gas and carbon monoxide gas, and right away I'm told that is an endothermic reaction. So remember, with Le Chatelier and equilibrium, endo-exothermic, we want to think about heat energy as a reactant or product. If something is endothermic like this, we are adding energy overall. Therefore, we can say that heat energy is like a reactant, okay? So I could rewrite it just like that. That may help us think about what has happened to this system. Okay, so you can see that the y-axis is concentration. Going along from 0 to 4 minutes, I'm at equilibrium. And then all of a sudden, my equilibrium gets broken. I start to form more products and consume more reactant. So what are some hypotheses? The question here is, what change took place at 4 minutes? What did we do to the system, to this reaction system, to cause this change? So what could we do to the system to consume more reactants and produce more products? We could develop some hypotheses. The first hypothesis I have is, well, maybe we added heat energy. Maybe we increased the temperature. I'm asking what happened at 4 minutes to break equilibrium. Maybe we increased the temperature. Increasing the temperature is certainly like increasing a reactant. Therefore, the system will respond by trying to decrease the reactants and make more products. And that's exactly what happens at 4 minutes. Well, what else could have happened to my system? I don't see any sudden big changes at 4 minutes, so it's not like I all of a sudden added more reactant or something like that. So that's not a good hypothesis. But what else could I have done? Well, I wonder if I could have decreased the pressure of the reaction vessel. Decrease the pressure. That's another thing I possibly could have done. How do I decrease the pressure of a reaction vessel? I could have increased the volume, right? Remember that pressure and volume, as long as everything else is constant, if I did not truly change the temperature, the pressure and volume are inversely related. So maybe this is happening like a syringe or something, and I can pull up or press down on the plunger of the syringe and get the pressure to change. Now here's something we've not talked about, and you guys need to get this down. Pressure changes. How will a system respond if we change the pressure? The system will respond by favoring the side that has more gaseous moles in order to increase the pressure again. Let me say that one more time. You guys need to get this in your notes. So Chatelier's principle tells us that for gases, if we decrease the pressure, the system will shift to favor the production of more gaseous moles. And it's that simple. Remember that the ideal gas law is PV equals nRT. Pressure and number of moles are directly related to each other, okay? So if we decrease the pressure, the system will shift to favor the production of more gaseous moles. That's something I could have done here at 4 minutes, right? I can see that the system responded to whatever stress I did. It's a mystery. The mystery is, what stressor did I add at 4 minutes? What would be a good hypothesis for a stressor I added at 4 minutes? Temperature is one idea. Increasing the temperature would shift the system to the right, make more products. So that's one hypothesis. My next hypothesis is that maybe I could have reduced the pressure. What will happen if I reduce the pressure of the system? The system will shift to undo that reduced pressure to get the pressure back to what it was before by making more gaseous moles. Well, which side of this reaction has more gaseous moles? The right side. The left side only has one. The right side has 1 plus 1, which is 2 gaseous moles, okay? So you all need to get that down, that changing the pressure, the system will shift in the direction that will undo that pressure change. In this example, if you decrease the pressure, the system will shift to favor the production of more gaseous moles. Of course, the opposite of that is true as well. You guys need to understand, if we increase the pressure, the system will shift to favor the production of fewer gaseous moles. It wants to relieve that excess pressure by making less moles of gas. And of course, that's not what happened here. So I know for sure that I didn't increase the pressure, or else the system would have shifted to the left. And that's not what happened at 4 minutes. I'm just asking what happened at 4 minutes. So I know that one of these things had to happen. How could I test to see? Well, I hope you guys understand that a temperature change causes a change in K. So what I could do is I could calculate the K before 4 minutes using these concentrations. Then I could calculate the K when equilibrium has been reestablished. Looks like equilibrium gets reestablished at about 8 minutes. That's when these concentrations become steady again. So why don't we see what our K values are? Well, an expression for K here, these all have a coefficient of 1, don't they? 1, 1, 1. So K is going to be really easy to calculate. K is going to be the concentration of product, Cl2, times CO, raised to the first power each, over the concentration of ClO2. So let's find what the K value is first. Let's see, the concentration of Cl2, that's about 0.09. The concentration of CO, this is a bit hard to see, but that looks like this is 0.7. That's not quite 0.07, so 0.068. If you're given a graph to analyze on an exam, it'll be much clearer than this.
First. Is that good?
That looks great, bud. Oh, I love it. Very, very good.
Now I'm going to show you.
Okay, don't forget to erase those. Divided by the equilibrium concentration of COCl2 at 4 minutes here. Looks like it is about, let's see, 0.04, 0.05 would be right here. That's in between. So maybe 0.055. It's really hard to see on this graph. But this would be the K value at 4 minutes using those concentrations before 4 minutes. I'm getting a K value of about 0.11. And now I can repeat that analysis for the values that occur at 8 minutes. So once again, Cl2 concentration, that looks like it's just about 0.11 times the CO concentration. That looks like it's about halfway between 0.08 and 0.09, so 0.085, divided by the concentration of COCl2 after 8 minutes, which is 0.04. And if I've done my math correctly, it looks like I have indeed changed my K value. In other words, my K value went up. Both of my products increased quite a bit and my reactant decreased quite a bit. So of course that ratio is going to change. What's the only way you can change a K value? It's to change the temperature. So I've just discovered at 4 minutes what caused this change, what caused the shift to the right. I must have increased the temperature. I must have added excess heat energy like a reactant, causing the thing to shift to the right, giving me a new K value. If the pressure had just changed, the K value would have been the same before and after. But I can clearly see that at 8 minutes, I get a new equilibrium with a new K value. Okay, so that's how I discovered that at 4 minutes the temperature must have changed. All right. I want to see if you guys could figure out now what must have occurred at 10 minutes and at 14 minutes. At 10 minutes, our equilibrium clearly gets broken. We establish a new one by 12 minutes. But then at 14 minutes, that equilibrium gets broken. So let's see if you can figure out what must have happened. Okay, so at 10 minutes, I hope it was somewhat easy for you to see. There's a big clue at 10 minutes. The CO concentration drops dramatically, instantly, quickly, in almost no time at all. So there must have been something to cause the CO to drop. I must have, at 10 minutes, We would say that CO was extracted from the system or something like that. Extracted or quickly removed. And that's pretty simple. If we quickly remove some CO, we take it out, what's our system going to do? That's a stressor. We've just reduced the amount of product. Our system is going to have to shift by increasing the amount of product again. It's going to have to shift to the right, and that's exactly what happens after 10 minutes. We consume reactants, and we produce products again, all right, until we reach a new equilibrium at 12 minutes, okay? So at 10 minutes, we quickly remove some CO. Did you guys figure out what happens at 14 minutes? Now this one is interesting. At 14 minutes, these all drop dramatically. What change could I have made to the system to get them to all drop dramatically at the same time? Well, these are gases. And what could I do to decrease their concentration all at the same time? I must have increased the volume of the reaction vessel. Again, if this is happening in a syringe, maybe I pulled back the plunger of the syringe and gave the reaction more space. Remember, concentration is moles per liter, moles per volume. I see that all of their concentrations drop dramatically. What's the only way I can change all of that if this is happening in a closed system? Change all of them at the exact same time? I must have expanded the volume of the reaction vessel, okay? And how can that help me think through the way that the system shifted? It shifted by consuming reactant and making more product. Well, think about what we said earlier. Think about the statement I wrote down earlier. Increase in volume equals a decrease in pressure. So I have caused a stressor to my system by decreasing the pressure. How will the system respond? It will respond by trying to increase the pressure again. The system will respond by doing the opposite of what was done to it. The system can't do anything about the volume of the flask. The system can't reach its hand out and change the volume. But what it can do is change the pressure. By increasing the volume, I have changed the pressure. I have reduced the pressure. So the system will try to increase its own pressure. How can the system increase its pressure? By making more gaseous moles, consuming reactants and making more moles of product, because the product side has more gaseous moles. It has 2 gaseous moles compared to 1 gaseous mole on the left-hand side. And that's exactly what we see happen. The reactant gets consumed, the product gets produced. So this is a great slide for you guys to study to understand all aspects of the Chatelier's principle. I know at 4 minutes something happened, and I was able to show that because the K expression changed at 4 minutes, between this equilibrium and this equilibrium, I know there was a temperature change. I know that heat energy, because it's endothermic, heat energy is acting like a reactant. The system made more product, it shifted to the right, so I know that I had to increase the temperature at 4 minutes. At 10 minutes, something else happened. Really simple, I can see that CO dropped. So the stressor that occurred is that I reduced the amount of CO, I reduced the amount of product. The system had to shift to make more product and consume more reactant. The system shifted to the right. So in both of these instances, the system shifted to the right. And then at 14 minutes, we saw that they all dropped with each other. Their concentrations all decreased. So I must have increased the volume. So right here at 14 minutes, my stressor was that I increased the volume of my syringe reaction vessel. When I did that, I decreased the pressure. Pressure and volume are inversely related for gases. By decreasing the pressure, the system shifted once again to the right to try to make more gaseous moles. It has more gaseous moles on the product side. So I changed the temperature. I changed the amount of one of the chemical species. I changed the volume. These are all really important stressors that I can do to the system. You all need to understand those and understand how the system responded to those. Okay? Okay, this is an old multiple choice question. We see that PCl3 and Cl2 undergo a synthesis reaction to form PCl5. It progresses for a time, so that tells me that I reach equilibrium. And then all of a sudden I inject additional Cl2. Which of the following graphs best represents the rate? So I'm looking at the rate of the reaction as a function of time. And notice that the rate that they're asking me about on these graphs is the rate of the reverse reaction. So this is actually pretty tricky. So the system reaches equilibrium, which means that the reverse rate is some non-zero amount at the beginning. Dynamic equilibrium, right? So right away I see that this first graph has the rate of the reverse reaction as 0 at the beginning. I know it cannot be that. So now I need to figure out which of these it is. So let's think about this. We're trying to, this question is complex because it's asking about equilibrium, it's asking about kinetics, about rates of reaction, because the rate of the reverse reaction is being graphed here. So let's think about this. If I add excess Cl2, I know that the system is going to shift to the right, according to the Chatelier's principle. Okay, so if I add excess Cl2, then I know that the system will shift to the right, and I'm going to be making more PCl5. Well, remember that rates of reactions depend on concentration, right, of chemicals. So the rate of the reverse reaction depends on how much PCl5 I have. And if I add excess Cl2, then I am forming more PCl5 slowly. And so I know that because I'm making more product, the reverse rate should slowly increase. And therefore, I get this graph right down here. So I know that this one is the correct answer. Now, I know it's not the middle two because the middle two show a quick spike. So I know that the answer has got to be D. It's got to be this last one, because I know that when I add Cl2, I'm going to be making more PCl5, and when I make more PCl5, I know that by adding more reactant, I get more product. And when I get more product, I know that the reverse rate, the rate of the reaction with respect to the product, the reverse rate, has to increase, because as my system shifts to consume the excess Cl2 I just added, I know I make more product slowly. Slowly making more product is slowly going to increase the rate of the reverse reaction, just like that. I would not expect to see like a quick spike all of a sudden in the reverse rate because the system is going to take some time to consume the excess Cl2. I would see a quick spike if I was looking at a graph of concentrations versus time, and if I had a line for Cl2, I would see a quick jump in Cl2, and it would go like this or something when the Cl2 is added. But I should not expect to see a quick increase in the reverse rate of the reaction. The reverse rate is proportional to the concentration of PCl5 that I have, and the amount of PCl5 that I have is slowly going to climb as the system responds to slowly consume that excess Cl2, according to the Chatelier's principle. So letter D, this last option, is the correct answer. Okay, so here we want to see, once again, we want to try to figure out what the three disturbances are. This is the same reaction that we looked at earlier. It looks like this time it's the reverse. So CO plus Cl2 forming CoCl2 as a product. I know that it's reversed this time because CO and Cl2 are decreasing in concentration while CoCl2 is climbing. So it looks like I reached my first equilibrium right here at about 7 minutes because the concentrations become steady. But then at 16 minutes, something happens. Something screws it up. Can you guys tell me what happens at 16 minutes? What disturbance or what stress did I add to the system? What is disturbance A? Yeah, the stressor was that I quickly increased or I added some CO reactant. You can see that it jumped really high all of a sudden. The only way I can get a high jump like that is if I, as the chemist, came in and injected some excess CO2 reactant into the system. How did the system respond? It should consume excess reactants and make more products, and that's exactly what happens. I consume Cl2, I consume CO, I consume Cl2, and I make more products. So that's what happens, and then the system reaches a new equilibrium at 20 minutes. And then at about 26 minutes, I get a new disturbance, disturbance B. What do you think happens there? Yeah, at disturbance B, you can see that all of them drop dramatically, and the system responds by producing more reactants, right? So what could I have caused? What could I have done? What disturbance could I, or stressor could I have put on the system that would initially cause them all to drop, but then favor the production of reactants and the consumption? You can see that CoCl2 as the product gets consumed. Yeah, I must have decreased the pressure or increased the volume. Probably I increased the volume because their concentrations dropped. Concentration is moles per liter. So I must have increased the volume of my flask. And you know that a volume increase causes a pressure decrease. Which way will the system shift if its pressure is decreased? It'll shift toward the side with more gaseous moles, this time to the left. It'll favor reactants. And that's exactly what happened. It made more CO. It made more Cl2. It consumed CoCl2. So the reaction shifted to the left. Okay. And then a new equilibrium gets established around 31 minutes. And then at 36 minutes, I cause another disturbance, disturbance C. What do you think happened for disturbance C? Yeah, probably I had some kind of temperature change. I know that there's probably a temperature change because I could calculate the new K value. We've done this several times. I don't really want to take the time to do it now, but I know that the K expression for this reaction is going to be concentration of CoCl2 divided by the concentration of CO times the concentration of Cl2, just like that. And I can calculate those anywhere here in the first 30 minutes or so, as long as I'm at equilibrium, which is marked at the top of this graph for you where the equilibrium is reached. But you guys should know it's when these concentrations are the same, or unchanging rather. So I could actually calculate the K value, and I think I would find that I got a new different K value here. Now I know that this reaction is exothermic, so I know that I have delta H here. So let's see, whatever change I cause in the temperature here at 36 minutes, I know that it favored the production of the reactants. I know that the system shifted to the left to make more CO, more Cl, and consume CoCl2. So it is as if I added excess product to shift the system to the left. So I must have increased the temperature there at 36 minutes, disturbance C. Okay, maybe it would be good for you guys to pause and find what the K value was over here. Find the new K value over here, see if they are different. And remember that the only way to change the equilibrium constant K is to change the temperature. The K here, and the K here for the first three equilibria states should be the same. This fourth one I would predict should be different. So you guys could try, if you wanted to go and calculate those. Okay, so the big idea here is that you can cause a stressor to a system and the system will respond by doing the opposite. I increase the temperature. In other words, I give it excess heat energy. The system will respond by consuming that heat energy, shift the system to the left. I add excess CO right here. The system will respond by consuming that excess CO. I shift the system to the right. I made more product right there. All right, so hopefully you guys are getting the hang of this Le Chatelier principle thing. Just two more examples. I know you all are getting tired of this, but this is, like I said, really important. Okay, so from 0 to time 1 here, I have some kind of equilibrium, and we can imagine that my equation is this. Just like that. And let's see, I wonder what disturbance I caused at T1. Any thoughts? Yeah, it looks like I dramatically increased the amount of N2 right here. And of course, that is going to favor the production of products. I've got to consume more reactants to undo that stressor I just did. And that's what I see. The reactants go down, the products go up. At T2, I have a new equilibrium. This new equilibrium, this time I see all of the concentrations go up. So at T1, I know that I increased the concentration of N2. I added N2. At T2, what change did I make to cause all of their concentrations jump? I must have decreased the volume, right? Once again, concentration is moles per liter or moles per volume. So how do I make that get bigger? I can decrease the denominator, and therefore all their concentrations jump. And these are gases, so what would I expect that to do to my pressure? Of course, a decrease in volume equals an increase in pressure. That's the disturbance that I made. So if I increase the pressure, which way do you think the reaction will shift? It should shift to decrease the pressure again. It should shift to favor the side now that has fewer gaseous moles. The right side has 1, 2, 3, 4 gaseous moles. Excuse me, the left side has 4, the right side only has 2. So I would expect that by me as the experimenter decreasing the volume, which we can see here in this sudden change, all the concentrations go up, I should expect that the system will respond by decreasing the pressure because I just increased it. This is the stressor I added. The system wants to respond to do the opposite of that stressor. It should shift to the right, making more ammonia. And that's exactly what happens after T2. The reactants get consumed and ammonia gets produced. And then at T3, I could predict that probably there's some temperature change because, and I know that there's probably some temperature change at T3 because there's no dramatic jump. They don't all change the same dramatically. So the only option is that there's a temperature change. And in this reaction, we're not told if it's endo or exothermic, so I don't know exactly what the temperature change is. But we can see that the system shifted to favor the reverse reaction, because the amount of ammonia now goes down and the amount of nitrogen and hydrogen go up. And actually we did see earlier, and we should know that this is an exothermic reaction, which means I can treat enthalpy or heat as a product. So what temperature change must I have caused at time 3 here to favor the reactants? I must have increased the temperature, huh? It is as if I added excess product. The system doesn't like that stressor. It wants to relieve that stress by shifting the reaction system to the left. Once again, if you like my dumb little marble analogy, it is as if I brought the thing from equilibrium up here to the product side. It's like I added excess product. It's like I brought the marble up toward the product side. So what's it going to do? It's going to shoot over towards the reactant side, isn't it? That's exactly what we saw. The reactants, hydrogen, nitrogen went up, while the ammonia went down. So I must have increased the temperature there. They all changed slowly and steadily. I didn't have a big dramatic change. I didn't like suddenly inject more nitrogen or change the volume of the reaction vessel or anything like that. The change is slow and gradual for all of them, so that's indicative of a temperature change. And I know that because this is an exothermic reaction and the system responded to my stress, whatever my stressor was, I know that the system responded by shifting to the left. Well, because it's exothermic, I know that, I must have added excess product to get it to shift to the left. I must have increased the temperature then. All right, just one more. Okay, so we could write an equation for this. I know that it's the synthesis of HI from H2 plus I2 to yield HI. I know it is that rather than the decomposition because I start with no HI, right? Okay, so equilibrium is reached at about 10 minutes. And H2 and HI are always, I'm using the same amount of them, and they have the same coefficients. They're always going to be corresponding to each other. And then let's see if we can figure out what happens at 20 minutes. At 20 minutes, I do something that causes equilibrium to shift. Well, pretty clear. It looks like I suddenly remove HI. So at 20 minutes, I suddenly remove HI. And which way would I expect the system to shift to reach a new equilibrium? The system must shift to make more HI, and that's exactly what happens. So I know at 20 minutes, HI was removed. That's the stressor I added. Then I get a new equilibrium for a long time, and then just after 35 minutes, I can see that something else happens. It affects them all very gradually. I must have caused some temperature change. I don't know if this is an exo or endothermic process. We could look it up, but we've seen this many times. They all start to change smoothly. I don't have any dramatic change like that, so it can't be a volume change or a pressure change that caused this. It must be a temperature change. And you can see that I'm going to get a drastically different ratio than I had back here at this equilibrium or even this one. Because these ratios are dramatically different. We could even calculate what they are if we wanted to, but yeah, at about 35 minutes before the new equilibrium is reached, I must have caused some temperature change that favored the consumption of HI, that favored the reverse process. Okay? Okay, so I want to get a summary of Le Chatelier's principle. A reaction system will always respond to a stressor to reestablish equilibrium. It will do this by doing the opposite
Are you teaching people?
Of the stressor. Possible stressors are change in concentration of a species. That one's simple. Volume or pressure changes. That one's a little more complicated. For gaseous systems, if the pressure is decreased, the system will shift to increase the pressure again by favoring the side with more gaseous moles. The exact opposite is true. If the pressure is increased, the system wants to remove that excess pressure, so it's going to shift to decrease the pressure again by favoring the side, reactant or product, with fewer gaseous moles. And of course, please remember that volume changes can cause pressure changes because pressure and volume are inversely related. And then finally, our last stressor is temperature. To do this, you're going to treat heat energy or enthalpy as a reactant for endothermic reactions, as a product for exothermic reactions. And then you're just going to figure out how the temperature change affects the reactants or products. I'm not going to type any more specific than that. That should make pretty good sense to you guys. You know that if you have more reactants, all of a sudden the system will shift to consume those excess reactants and make more products. So if we treat heat energy like a reactant or product, endothermic reactions, we treat it as a reactant because we're adding heat energy in overall. For exothermic reactions, we treat heat energy as a product because energy is given off overall. And then we can use that to help us figure out how the temperature change will affect the system. All right, we will review this some more. Watch this as many times as you need to until you have it figured out. Email me questions you have, and I'll talk to you guys later.